So here we are. This is the assembly language course, and we're going to go through, today it's going to be binary and data representation. So let's start with that. And we're down, I got some slides from this chapter as usual. Just put them there, that should work. Okay, so we're going to talk about number bases and unsigned integers and some bitwise operations here. So, you've already started playing this binary games, hopefully last time. So I said last time we talked about nibbles, bytes, and hexadecimal, and this time we'll talk about modular arithmetic and XOR, continuing this project. All right, so binary integers, unsigned binary integers are easy to understand, and that's what we talked about in that lesson last time, where you just count from 0 up to some maximum number. None of them are negative. But if you're going to have negative numbers allowed, then here's how they do it. See, the leftmost bit is treated as -1 if it's a 1, and all other bits are treated as 1. So you'll have the negative of the most significant bit, and then all the rest are positive, and that's why the end result will be negative. Because even if all the rest of them are 1, they'll always be smaller than the most significant bit, which is negative. So that's the 2's complement. So for nibbles, 4 bits, it looks like this. You have 0 through 7, just like we had it before, but the numbers that would be considered above 7 for an unsigned integer are now interpreted as negative numbers. So you count the leftmost bit as negative, so this is -8, this is -7 because you have a -8, and then you add 1, -6 and -5, and all 1s is -1. So that's the 2's complement way to represent a negative integer with a binary series of bits. So if you want to find the negative of a number, you flip all the bits and add 1. So if you have 13 here, then you want to make the negative of it, so you flip all the bits, so all the zeros turn into 1s, these 2 1s turn into 0s, the 0 1 becomes a 1 0, and then you add 1, and if you add that all up here, -1 times 2 to the 7 plus 2 to the 6, 2, 5, 2, 4, and so on, you'll get -13. So that's the plan. That's how the 2's complement works. So in C programming, int is a signed integer and unsigned int is unsigned. And this is how they're actually stored. So here you can put out a number that's -100, and you can print it either as a signed integer or an unsigned integer, and you'll get 2 different answers. You'll get -100 if it's a signed integer, because this is defined as a signed integer with a negative, but if you can interpret the same pattern of bits as an unsigned integer, and then it's this huge number, which is going to be approximately 2 to the 32 minus a little bit. So that's an important thing to know, and I mentioned this before. This is the fundamental reason we're able to hack into machines so easily, that the bytes are not labeled with any kind of type of data, so that all you have is a bunch of bits, and they could be an integer, they could be a floating point number, part of a music file, executable code, plain text file, and there's nothing in the bytes that tells the computer how to interpret that data. It can just interpret it all different ways, so we're going to be able to, as we have, inject bytes that the computer is interpreting at that time as text, and then execute them as executable code. All right. So you can do arithmetic on these things. You can add 2 things like these. You're going to add them together, and this is going to be a negative number. So you're going to 0 and 1 gives you 1. 1 and 1 gives you 0, and you have to carry a 1. That puts a 1 here, and 0 and 1 gives you 1. So there you are. You get that answer. And I think in this case it'd be the same for whether it's signed or unsigned. It won't matter. Here you're going to take this and subtract 11. So now, obviously, you could just do it here. 1 minus 1 is 0, 1 minus 1 is 0. So you know the answer is 0, 1, 0, 0. But here's the way you would do it formally. To do this negative thing, you would now turn this, you would negate this. So you flip all the bits and then add 1. So you flip all the bits and add 1, and then you do addition. So now you have 1 and 1 adds up to 2, so that's 0, and you carry a 1. 1 and 1, 0, and you carry another 1. 1, 1, and 1 is 3, so that's a 1 and you carry a 1, and this 1, 0 is going to be a 0 and carry out a 1, so you have one number that comes off the left here, gone, so you end up with 0, 1, 0, 0. All right. And here's another one. I'm going to take this number minus that number. So I have to negate this number, and that's going to be 0, 0, 1, 0, and then add 1. And now I just add these three. So 1 and 1 is 0 and carry a 1. 1, 1, 1 is 1 and carry a 1. 1, 1 is 0 and carry a 1, and you get 10, 10. So, all right. And here's another one. You're going to add these two numbers. So you take 0 and 1, that's 1. 1 and 1 is 0, and you carry a 1. That one goes here, and that one goes here, so you get that. So you can do math in binary the same way you do it in base 10 formally. You just have to get used to the fact that there's only ones and zeros. So let's take a look at a Kahoot. 4A should be here. All right, I guess we got the people that are coming. All right, so what is that number in decimal? All right, we talked about this. For this number is the number of 1s, 2s, 4s, and 8s. So that's 4 plus 8, or 12. All right. 15 would have to have more 1s in it. All right, what's that number in decimal? 0b indicates binary, and 0x represents hexadecimal in Python. I'm using that convention. That's 14. F is 15, E is 14. All right. Not a popular answer, but it is 14. E is even. There's one possible bigger single hexadecimal byte, and that's F, which would be 15. So, all right. All right, what's the largest value you can store in a signed byte integer using 2's complement? It's 127. The left bit has to be 0, or it's going to be negative, and if all the other bits are 1, you get 127. Let me just talk about that. I'm seeing nobody got that right. That's troubling me. So let me bring in a text. All right. I'm bringing a good example. All right, so if you consider it, if I have, all right, that's 1 in a byte. And if I do this, that's 15. Well, hopefully remember that. We've talked about that before. And if I try to make the largest possible, now remember, if I have a 1 here, that's going to be interpreted as negative. So every number starting with 1 is negative. So I have to have 0 for positive numbers, and then I just have to fill in all the rest with 1s. So that's the largest possible value. And if you count this, this is the 1s, 2s, 4s, and 8s, 16s, 32s, 64s, and 128. So that 0 would stand for 128. So you know that in unsigned numbers, this number would be 128. So the number just before that is 127. That's an easy way to figure it out. Now you could take 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, and you would find that it's 127. But it's much easier to detect that it's 1 less than this number that's easy to figure out. So that's the largest possible number you can encode with 1 byte in 2's complement signed integers, because all the ones bigger than this have a 1 on the left, and that makes them negative. So I hope that helps. All right. All right. All right. Well, I see that people are not remembering their binary. I hope the point of that binary games project was to give you some practice and hopefully get you remembering how binary works. We'll carry on. All right. So then there's overflow, which is the main security problem with integers. So if you have an unsigned nibble, it can go from 0 to 15, and then if you add more to it, it wraps around to 0. Some bit it progresses off the left, but it vanishes because you're in there's ring math. So that's one form, overflow. You keep adding numbers until it gets too big, and suddenly it wraps around like an odometer and gets small again. If you have signed numbers, then the overflow happens here. You can count up to 7, but when you add more to a 7, it becomes a negative number instead of a positive number. So again, you get the wrong answer. Right? And then there's bitwise operators. So you can AND 2 bits. And what that means is they both have to be 1 for the answer to be 1. And this is easier to understand if you think about 0 as false and 1 as true. A and B, if they are Boolean variables, they both have to be true for the combination to be true. So this is what AND does. If either one of them is 0, the answer is 0. Only if they are both 1 is the answer 1. That's AND. Then there's OR. OR, if either one of them is 1, the answer is 1. And if both of them are 1, the answer is 1. So only if they're both 0 do you get an answer of 0. So it's just the inverse of AND, essentially, the opposite. And it, again, it's easy to understand if you think about these as logical variables where 0 is false and 1 is true. Although C does not have Booleans, but you can think of it that way. And then there's exclusive OR. And exclusive OR means A, X, or B. This means one of them has to be 1, but only 1. So if you have 0, 1 or 1, 0, the answer is 1. But if you have 1, 1, the answer is 0. And if you have 0, 0, the answer is 0. And I mentioned in the world of cryptography, this is the one you always use because this one does not destroy information. If you think about it, if I feed in a bit stream for A that is half 1s and half 0s, and a bit stream for B that's half 1 and half 0s, and it's all random, then I'll end up with a bit stream that is still half 1s and half 0s. And that means if you calculate the Shannon entropy, or the information content, it's the same. So an XOR operation can be reversed. In fact, doing a second XOR with the same numbers will reverse it. But if you look at these destroy information. If I start with half 0s and half 1s, and I XOR it with OR it with half 0s and half 1s, I'm going to end up with 3/4 1s and only 1/4 0s. And Shannon proved you can take the probability of outcomes here and calculate the information content. This has destroyed information. Consider the case where I had some transformation where the answer was always 1. Then I would destroy all the information. You'd lose all the patterns of both bit streams. You just have a bunch of 1s here, so it should be kind of intuitively obvious that having an uneven balance here is destroying information. So this transformation cannot be reversed and is therefore not much use in cryptography. It destroys information. But this transformation does preserve information, and that's why almost all cryptographic systems use XOR as part of them. They use other things too, but part of it is just XOR. It is a transformation from one string of bits to another string of bits that can be reversed. All right, and then you got NOT, of course. NOT just flips a bit. So 0 goes to 1 and 1 goes to 0. All right. And then you can do bit shifting. So if I have 13, 13 is this in binary, 1101, and now I can shift it to left 3, and that means you shift these bits, each bit's to the left, and you fill in with zeros on the right. So the 1101 moves over here, and that's going to be the same for unsigned integers as multiplying it by 8. Each time you shift it to the left one, you've doubled it. Because each one of those bits, if it used to be here, standing for the number of 1s, now it's here, standing for the number of 2s. And if it was here, standing for the number of 8s, it now moves over to stand for the number of 16. So every left shift doubles a number, so doubling it 3 times, it multiplies by 8. All right. Then there's a logical right shift, which is the same thing. You're going to shift it to the right, padding it with zeros. So this 1, 0, 1, 1, 0, 0, 1, 1 shifts to the right, twice, I guess, is going to fill in with zeros here. The 10, 11 is going to move here. These 1s are going to fall off the end and vanish. That's a logical right shift. Now, an arithmetic right shift will prepend a copy of the most significant bits in order to preserve the signedness. So if you arithmetically shift this to the right, then over here, you'll have the same thing, 10, 11, 0, 0, but instead of having zeros come in from the left, you're going to copy the original leftmost bit, so you'll have 1s come in from the left. That's another way to do it. All right, and so if you do a logical right shift for unsigned int, that's what this does, greater than greater, that's a logical right shift. And here's an arithmetic right shift is what it will do for signed ints. So you have an unsigned value and an int value. The same operation here will choose the correct one based on whether it's signed or unsigned. The signed ones will do the arithmetic right shift to preserve the sign. The unsigned it will just move the bits like they were dice on a table. All right, and we talked before, we'll talk about more of these in the binary games. And then there's byte order for integers. This is endianness, and it's one of the irritating things about assembly language in the Intel processor. If I have a 16-bit integer, then there are 2 possible ways to do it. One is to put the high-order byte first and the low-order bit second, and that would be more natural. When you write numbers, you write 114. You put the most significant number first. So this would be the number of 256s, and this would be the number of 1s. But in Intel processors, it's little endian. So it puts the least significant byte first, followed by the most significant byte, which is pretty annoying, but that's just the way it is. All right, x86 uses little endian. So if you define this with AA, BB, CC, DD, and then print its memory address and value, you'll see it's actually stored. The AA is most significant, and then BB, CC, DD, these are least significant. It's actually stored, if we go to the bytes one by one, this way, DD, CC, BB, AA, backwards. A very strange thing to do, but that's the way Intel processors work. So same thing here. This would be big endian, but this is little endian. All right. And then, of course, not everything is integers, so you can have floating points with a decimal point here, although they call it a binary point for binary. And now you'll have, this is one way to do it, if you wanted to settle for just 2 digits here, so you can only represent like quarters, quarter, half, 3/4, and whole numbers are all you can have this way. This is one possible way to do it with a fixed point representation, but nobody uses it that way. What they use is floating point representation. And in floating point, you have a sign bit, then you have an exponent, which is 10 to the this, and then you have the other bits. So it's going to be some number times 10 to this. And therefore you have limited precision, but you can express numbers up to a really high total or a negative total. So that's what those are what floating point numbers are actually stored as. So let's try another Kahoot for B. Well, I observed that binary is not very popular. We'll carry on. Right, so what is it if you combine those two with AND? Good. You get zeros because you just do it bit by bit. So this is a 0 and the corresponding one here is a 1. They're not both 1 and they have to both be 1 and this is 0, so it's going to be 0, 0, 0, 0. And means both of them have to be 1 in order to produce 1, otherwise it's 0. So that's 0. All right? All right, how about an XOR with the same numbers? Yeah, very nice. Because for XOR, you have to have a 1 and a 0 for the answer to be 1, and you always have that. The first three are 1, and the matches are all 0. The last one's a 0, and the matches are 1, so all of them have the property that there's 1, 0, and 1, 1, so all of them turn into 1s. All right? Good? All right. And what's that? Using arithmetic right shifts. It's going to be this yellow one because arithmetic right shifts, you shift everything to the right and you copy the most significant bit over and over. So you're going to start with 2 1s, and after you shift twice, you're going to have 4 1s. And this is the only one with 4 1s. So you'll have 4 1s, 2 0s, and 2 1s. There it is. All right. So, all right, good. I've recorded the winners. All right, and I observed that a lot of you are not participating in the Kahoots and don't seem to like binary much. This is unfortunately a common situation in America due to the way we teach mathematics. A lot of people develop a phobia about it. And I'll mention if you don't want to do the binary, try and do these binary games project, but of course there are other projects. Remember, there's plenty of extra projects. So if you really hate it, you can just skip it and do more other projects to get some extra credit points to make up for it. So if you don't make much progress learning binary now, you can move ahead. You'll eventually need to learn it, but I understand if it takes more time. more. You might have to knock your head against it more times before you get good at it. So let me stop